And so this is mostly a CPU-focused talk, but just as a teaser for if you are on other supercomputers, Julia has excellent GPU computing capabilities. But today we're going to focus on Okami and we're going to focus on A64FX. So my co-speaker, Mose, is a research software engineer at UCL. And let's get started. So why do we care about Julia? Why do we why have I been drawn into working on Julia? My background has been originally I was a scientist working on cognition and building models and doing robotics, and I always felt like I needed a language that was both flexible and let me express the problems that I wanted to solve. And so I 2014 discovered Julia, and it somehow just clicked in my head. It made me happy. I didn't feel like yelling at my computer as much. Now I yell for different reasons, but that's fine. So here on the right-hand side, we have a little bit of a Julia snippet. It's called calculating the Mendel function. And you see the syntax is like a good mishmash between Fortran, MATLAB, and Python-ish. But so we don't have curly braces, you don't need semicolons, so forth. One important note that sometimes trips people up is indexing starts at 1 as it should be, whereas you can then do offsets from 0. Julia is index agnostic to some degree, but indices indexing into elements starts at 1. It has the typical features that we expect from a modern language that came about in the last 10 to 15 years. It is open source. It has a very permissive license. You can fix bugs. Well, there are bugs, but you can also fix them. In contrast to other languages that I won't name, where some people I know are waiting for bug fixes for the last 10 years. It has a built-in package manager that is really nice. Every time I have to switch to something else, I scream in frustration. And while it is geared towards interactive development, people are also using it to build HPC applications. Nowadays, there are big projects that use Julia to do climate science, to do material science, to solve PDEs, ODEs, scientific computing in general. The unusual features it has is for a dynamic high-level language, it has great performance. I always promise that you can get within 2x of C without trying, and then faster with trying. But if you write slow code, you also get slow performance. So it's not a magical thing. It still needs performance engineering. But what is very attractive for me and for other people is that you can stay within the same language while you do performance engineering. You don't incur this moment where you're like, well, this is as much as I can do. Now I have to switch to C, C++ in order to solve my problems. It has a very unusual style of compilation. It uses something that we call just-in-time ahead of time. So sometimes when you load Julia, you will notice that the first execution of a function is slightly slower. That slightly slower is a moment where Julia analyzes your function and compiles it using LLVM. Most of Julia is indeed written in Julia, even part of the compiler written in Julia, and it has very powerful reflection and metaprogramming capabilities because if you look very closely under the hood, it is kind of a Lisp. So this is one of the benchmarks, and of course, like take every benchmark, especially if they're coming from a particular group of people, with a big pinch of salt. What we strive to do when we wrote some of these benchmarks is that we try to implement the same algorithm and the same structure. So it's not necessarily how can one implement the best Fibonacci or quicksort, but if I'm using a recursive structure, what is my performance pattern I can expect? What is the penalty of function calls, right? That is the kind of thing we wanted to investigate. And generally speaking, all of these numbers are normalized towards C. And then Julia is here on the first column. Then you have Luajade, Rust, Go, and Fortran. And I need to update this graph at some point. But what we like to see is that Julia is in a relatively low spread around C. It is fast, and it is atypical for its language family in that sense. Okay, so because I'm a computer scientist now, a quick detour into what makes a language dynamic, why it's actually important to think about if you're choosing the language for your next project, what are the kind of feature sets you might want to have? And when people say dynamic, they commonly just refer to the type system. So you can have a variable x, and x can be a string, and then 2 lines later, it can be an integer. And so when people say static, they say, well, the types are checked before runtime and variables can't change types. Whereas dynamic languages, types stick around during runtime. You can do introspection. You can say, what is this value? What is the type of this value? Oh, it's a floating point number. Let's do something with it. But there is a second part to this story, which is, can I add code? When you start executing a program, is all of the code that you can ever use given to you at this one time, or can I add code over time? And so this is what I call closed world. The code is given, and open world, the code can be added at runtime. And if you want to have a litmus test and see whether or not a programming language is dynamic in that sense, you can see if it has a construct that people call eval. Can I evaluate code at runtime? And then there's this other thing that people sometimes forget about, which is we have data layouts, we have structs in programming languages, right? We have classes in Python and Ruby and Julia. And the question often is, can I change the layout of that struct at runtime? Can I change the type of a field? Can I add new fields? Right, so this is an example of dynamic code where x is first a Boolean and then x becomes a string later on. But if we look at Julia and we try to look at these 3 axes and we say, we notice that Julia has a dynamic type system, which makes it the compiler doesn't get into your way, but you don't get error messages immediately. You get error messages at runtime, not at compile time. That's a trade-off. It has open world semantics, which make some fun programming possible. But, and this is one of the big buts, struct layout is indeed static. Once I declared a struct, I can't change the fields. Well, I could say that a struct contains a boxed variable somewhere in the heap, and then I runtime and inspect the variable. That is feasible. But I can also say that the first field of struct A must be an integer. And because we have that knowledge, we can do things that traditional static languages can do, like allocate an array of structs and have all of the structs be one after another. If you do that in Python, you always get a pointer in direction. And so about 5 years ago, I would say Julia has a really stupid compiler, but a quite clever language design. And we've just been adding smarts to the compiler ever since. Right. And so this language design really leads to efficient execution. And if you want to learn a little bit more about this, I have a reference here to a paper. And generally speaking, we've been working on making the compiler relatively extensible. And one driving factor of this was that over the last years, GPUs have been really become the forefront of development. And so we added support for CUDA, AMD, Intel, Apple GPUs through the LVM compiler. And so we have a general infrastructure for how to retarget the language and extend it to different new kinds of accelerators. So, well, a little bit about what we do traditionally in Julia. You will find that people encode behavior in the type domain. So as an example, I can call the function transpose on a matrix, and it will not actually do the transpose in that moment. It will just say, well, I now have a transpose type, that contains whose element type is float64, and the data stored is stored as a matrix of float64. And so we can encode through these abstractions generic behavior. We can then use a just-in-time compiler to specialize these functions to produce optimal code. And we can use multiple dispatch to relatively easily choose optimized behavior. So as an example, if I have a multiply and one of my matrices is a transpose matrices, I will eventually end up in this function call, mul exclamation mark, that then will call into a class. It might be your vendor class if you're on Okami and you want to use that one, or it will be by default open class. Right. So just to give you a little bit of a hint of how Julia works under the hood, we start with the typical things, and all of these green things are kind of, that is what Julia's job is, and the blue part here is what LVM's job is. But we start with whatever you've written as code. And then we will parse it, we translate it into an abstract syntax tree, and then we will start simplifying this abstract syntax tree through lowering, run optimizations, inlining, type analysis on top of it. We end up with this typed AST, and we will see a couple of examples later on, and then we will do LVM cogen over them. This will leave us with LVM IR, which we then hand off to LVM. We have a couple of Julia-specific optimizations passes, but generally speaking now, most vendors these days, including Future, work on LVM and improve LVM continuously, and we've seen improvements over the last release cycles. So as an example, we asked Eva to install the current development version of Julia on Okami because we did the switch from LVM 13 to 14, and it improved code generation for vectorization and for half precision. This leads to something I quite like, and especially in a language as dynamic as Julia, it's really helpful to have ways to figure out what is the code I'm actually running. And I don't know if you have ever had the pleasure of calling obstamp on a C++ binary and then trying to figure out which line of code what is the assembly of the code you're running. Of course, nowadays Godbolt exists and makes this much easier, but we have these kinds of reflection mechanisms built into the language. And so you can ask, which function am I about to execute? You can say, can you drop me into an editor and I can edit this function, please? You can look at the lowered code. You can look at the type invert IR with that code one type and that code type, and all of these weird at symbols. If you haven't used Julia before, these are so-called macros. There are functions that transform from syntax to syntax. And then at the end, we can do LVM IR. We can introspect what the LVM IR for a given function is. And then in the end, we end up with native code. And on the left-hand side is, if you are a person who enjoys messing about with systems, these are all of the ways where you can inject code into this pipeline. And so you can look at a function signature and you can generate the body at function if you want to. If you need some LVM intrinsics because you're doing something very specific and you want to use the hardware to the utmost, you can use directly LVM call. If LVM doesn't even have a representation of the assembly that you want to emit, you can just embed assembly. But you don't need to. That's the important thing. I'm telling you these things so that when you have an understanding of some of the things we will look later at, but also so that you have starting points to start asking questions about why is my code not performing as much as I think it should be. Often in HPC, we don't code in isolation. We code with a lot of libraries that are being used. And so we couldn't have gotten where we are with Julia now if we didn't have a foreign function interface that was very fast. And so you can call C and Fortran libraries that export an API, and there's documentation how to do so. But sometimes writing these foreign function interfaces can be very obnoxious, so you can do an automatic wrapper generation with clang.gl, which is what I normally do, which will take a header file, it will analyze the header file, and will generate Julia functions that then call these C functions. There's also a little bit of a magic trick where you can take a Julia function, you can produce a C function pointer from it with the macro add C function, and then you can give it to C code and you can use that to call back into Julia. Just be a little bit of careful. If you're not on the upcoming Julia 1.9 release, you can only do so from within a Julia thread. In future releases, you can do it from any thread that you're using in the system. But when you're doing this kind of interacting with C and Fortran, you always have to be a little bit careful because Julia is a garbage collected language. And that means that if if you're handing a pointer to C and the garbage collector doesn't see that you have done so, it might free the object while the C code is still trying to manipulate it. So an example of this would be from one of the libraries I work on, ucx.gl, where as an example down here, we have this gc.addPreserve, where I'm going to tell the garbage collector this buffer object must be rooted, but then I will obtain the pointer of the buffer object. And now as long as the scope of this begin end block is happening, the object doesn't get freed. Similarly here, you can see how I use the addC function to generate a callback and then pass that callback to a UCP function, and that is going to then invoke it later on. Also, if you have any questions, I think Mose is in the chat. You can just start asking them, and then towards the end of my little introduction, I can take a break and start answering some questions. The exclamation mark is pure convention. It means this is going to modify. It's going to mutate. That's just a nice convention we have. A lot of libraries follow it. That just means one of the arguments, most often the first argument, is going to be mutated. But it's not checked. But what about binaries, right? I think a lot of people have bad experiences with having to build native libraries and integrate them into another language. We invest a lot of time and energy into an infrastructure we call Binary Builder and Yggdrasil, where we provide binaries for Windows, macOS, Linux, FreeBSD, for many different architectures. Basically everywhere you can install Julia. We also provide binaries for common dependencies. And one of the reasons why we do it as a binary delivery service and not as a system of build scripts that we expect to run on the user system is because we can't ever assume that a compiler is available on the system. These are called artifacts. They are immutable. They are platform-specific archives. They greatly help in reproducibility. And if you want to know more, there are a bunch of links here. But of course, the question is, I'm on an HPC system. Everything is a little bit different than on my laptop. I must use the HPC or the Gray or the Future compiler to get best performance, or I have specific versions, yada, yada. How do I integrate these into Julia? And while these GL packages that we're using to deliver the binaries exist by default, everything is overwritable, exchangeable. Most packages have some way of saying, no, use this instead. And then if you have a dependency where you want to use something pre-built and you're sure that everything will work, you can always opt out. We have some long-term plans, but nobody has been really had the time to work on this, to integrate with HPC-centric build systems like SPAC. We're always looking for people to help out. So if that's something that interests you, chat to us offline. Now, taking a slightly different tack, I wanted to highlight some work of a colleague, Milan Klöver. which really piqued my interest in the A64FX that is available on Okami as a CPU, and that is the potential for doing interesting things with mixed precision computing. The A64FX is the first real processor that we have access to that has high performance half precision. And so Milan wrote this shallowwaters.gl code, which is an open source computational fluid dynamics code written in Julia. And one of its cool features to me is that it's type agnostic, type flexible. So you can put in a numeric data type that does doing compensated summation for low precision. And on an A64FX system, I think we were testing this on Isambard in the UK. We did indeed get about a 4x speed up with float 16 and the 2x speed up with single precision. And it will use half and float 16 interchangeably. And one of the interesting, and these are like the results, and I always like computational fluid dynamics because you get pretty pictures, which if you're working on compilers, you don't get pretty pictures. Is one important factor is that indeed, if you're doing it correctly and you're accounting for the fact that you're doing reduced precision arithmetic, you indeed can get qualitative equivalent results between float 64 and float 16. And so this is one of the test cases, and I show, okay. And really here the message is that the bottom is the float 16 simulation and the top is the float 64 simulation. And it evolves pretty much indistinguishable. These are the performance results that Milan observed. And so float 64 is the norm here at the bottom, and you can see the spread when the data size becomes larger. Performance, because you're hitting the bandwidth benefits you get with half precision increase. So performance, the speed up increases as well. And then of course, because we're doing half precision, we actually need to do compensated arithmetic. So the orange and the red line is compensated versus uncompensated. And then you can also do mixed. And all of this from pretty much the same code. Right. The only thing here really changed is what's the input data format telling it, oh yeah, you want to use half precision, so forth. Now, this is just as a quick excerpt how you can check how float 16 as an example is implemented in Julia. Right, we have this abstract type number, subtyping it to real, then we get an abstract float, and then we get primitive types that are implemented by the compiler and the runtime for the different sizes that we care about. And there's also a float 128. And then you can check as an example that the cuberoot function, it has different specializations, and those specializations are for big floating point numbers, float 16, and so forth. Now, at this point, I will hand over the screen to Mose, who will talk about some of the performance numbers we got on Fugaku. Mose, you're still muted.
Yeah, I was trying to find the button to unmute. Can you hear me well?
Yes, we can.
Okay, cool. Okay, so I need to share the screen, I guess. I lost Zoom.
While Mose is setting up, does anybody have any questions? Right, so Hans asked whether or not what high-level software design looks like in Julia. Are the libraries examples? I would say it is, on the one hand side, I think it is crystallizing in my head what it's supposed to look like more and more. but there are different playgrounds, different people trying out different ideas. Climber, the MIT Caltech climate science program, is writing a large-scale climate global circulation model in Julia with many different components. And so I think that is one of the biggest code bases that is openly available right now, and you could get inspiration there. How does Julia compare to other languages like C++, Rust in terms of memory safety? I was going to talk about this a little bit later. Generally speaking, as an example, we default to bounce checking. So if you're indexing into an array, we bounce check that access. Some places you can opt out of that mechanism if you don't like it, but that is something we generally speaking do. So it's a managed language. It has a garbage collector. So I would say it's not quite like Rust, but it's also not C++. Yes, so HPC support for communication libraries, that's what Mose is about to talk a bit.
Right. Can you hear me?
Yes, we can.
Okay, cool. Sorry, I had to restart Zoom. So yeah, I will talk about some benchmark measurements that we did on Fugaku. And I guess I don't need to explain what Fugaku is, but in case I need, Fugaku is like the big cousin of Okami. It was until a few months ago the first supercomputer in the world, at least according to the top 500 list. And it's based, of course, on A64FX. And we wanted to try out Julia on this machine and see how it fares. So first thing that we look at was BLAS functions. So like, can we implement a BLAS function in Julia and see and compare it with optimized libraries? So for example, I will show you in a bit, but for example, Fujitsu provides a library called Fujitsu BLAS for doing BLAS operations on A64FX, but there are also other optimized BLAS libraries. So BLAS, in case someone doesn't know what it is, BLAS is a collection of linear algebra routines. For example, there are different groups, let's say, of routines. The level 1 is vector-vector operations, and then there is level 2, which is vector matrix operations, and then level 3 is for matrix-matrix operations. And so, for example, we implemented this very simple function in BLAS. It's called AXPY, which basically does the multiplication of a scalar times a vector plus a vector. So this is why it's called A times X plus Y, AXPY. So this is implemented in Julia like this. And you can also notice from the definition of the function that here I'm not specifying anywhere the data types of the input, because as also Valentin mentioned in the Shulowot example, in Julia we can write type generic code. So we don't specify the code of in the definition of the function, but the compiler will optimize the code when it will run the code when you provide the input data. And then this is a simple for loop, nothing special. There are just a couple of macros to say you can apply SIMD optimization, and we are controlling that we are within the boundaries of the vectors X and Y, so you can remove the boundaries checks. So this is the Julia function that we wrote and then compiled to native code by LLVM. And we compared it with this function, which is simply calling into the C BLAS library, which can be Fujitsu BLAS and the others. So what we get? I hope you don't see the bar here, but anyway. So this is
it looks good.
Okay, perfect. Because I have the zoom bar at the top and I don't see the title, but I believe this should be the single precision AXPY. So the blue line is Julia, and then there is also Fujitsu BLAS, which again is the vendor BLAS on A64FX. Bliss is another popular high-performance BLAS library. And then there is also OpenBLAS, which is a popular, not super optimized open source library for BLAS. And ARMPL is the collection of mathematical libraries by ARM. Yeah, you can see that Julia gets the best performance overall, like it has the best, the highest peak. And also you have, for the rest in general, it's comparable with Fujitsu BLAS. Also, Bliss is pretty good performance, at least for larger vector sizes. Instead, OpenBLAS and ARMPL really struggle. I should note that I compiled OpenBLAS with GCC 8.5, I believe. It's written in a paper that we published a couple of months ago. So I had some problems compiling OpenBLAS with the Fujitsu compiler. I reported this issue to the OpenBLAS developer. That has been fixed afterwards, but not in time for the paper, for the publishing the paper. So yeah, so this is really not super optimized, the OpenBLAS version, but this is what I got anyway. So this is single precision, but we can do the same also for double precision, and the results are pretty much the same. And as a sanity check, you can also notice that the peak performance here is about half of what I got for single precision. And since this is Julia and Valentin already talked about the ability to generate also code for half precision, we also did this performance comparison for half precision, but unfortunately we don't have the half precision versions of all the other BLAS libraries. So in this plot there is only Julia, and again the peak performance is about 4 times the performance as the double precision and about double as the single precision. So everything checks. What else? Also, since we got access to Fugaku, we wanted to see how Julia fares on a real world, very big machine in terms of distributing the programs using the MPI protocol. So MPI is the standard, de facto standard protocol for communication in parallel, very large scale parallel applications. It's everywhere in all HPC facilities. And there are usually optimized libraries provided by the vendor or the system. Which is the case, for example, on Fugaku. There is a library called the Fujitsu MPI. But there are also other implementations. So for example, on Okami, there are both NVA Pitch 2 and OpenMPI. But here we focused on Fujitsu BLAS, Fujitsu MPI on Fugaku. So in Julia, we can simply call the external library using the MPI.jl package. This basically constitutes a high-level wrapper for the MPI functions. And you can see here an example of a ping pong implementation. Ping pong is simply sending and receiving some chunks of memory between two nodes, two different nodes. MPI.jl is also one of the oldest Julia packages, just to mention that there is a long-standing relation between Julia and HPC. And we compared performance of some Julia code using MPI.jl with the performance benchmarks done by Riken, the institute running Fugaku. So for example, this is the ping pong latency. You can see that there is a small overhead for smaller messages sizes, but then when you increase the size of the message, which is what you want anyway to do when to get the best throughput, Julia and the benchmark from Riken are pretty much the same. And next should be the throughput. So this is basically the inverse of the previous plot to show that at larger sizes, Julia is within, I think the peak throughput is within 1%, less than 1% from the performance supported by Riken. So here we wanted to show basically that using MPI.jl has a very little overhead in doing large scale applications. Well, ping pong is only 2 nodes, but then we also, yeah, I don't see the title of this.
384 nodes, 15,000 ranks.
What operation is this?
Already is.
Already, so okay, thanks. I don't see the title. Okay, yeah, so this is on almost 400 nodes using 1500 ranks. So it's decent size, I would say. And yeah, again, we can see that above 4 kilobytes of message size, the latency is pretty much the same. There is again a small overhead for smaller message sizes. And this is latency for some other collective operations. Again, we can see the same pattern, small overhead for smaller sizes, and then you're pretty much on par with the directly calling the C function, the C library. And this is the reduce operation, which is fun because apparently Julia MPI.jl has a smaller latency. I believe this is due to the fact that in these benchmarks, we didn't implement cache avoidance. So, and L1 cache of the A64FX is exactly 64 kilobytes. So I should try to implement at some point the cache avoidance for in this benchmark and try to run again the reduction here to try and see if we can like get again Julia above the C line, which is what we expect for smaller sizes. But again, for larger sizes, we are pretty much on par. And the summary of, well, this is more the opportunities of improvements of using Julia on A64FX is that, first of all, Julia is really not optimized, like Julia itself is not optimized for A64FX. And everything is done through LLVM. And for example, Valentin already mentioned, we noticed that switching from LLVM 13 to 14, we got a huge improvement thanks to the work of the ARM engineers in LLVM compiler. Julia is a JIT language, so it does compilation on the fly when you run the code for the first time in your session. And compilation latency in general in A64FX is very bad. It's pretty slow at compiling. So a JIT language is very hardly hit by this. But there is a lot of work to reduce the compilation latency. I will also mention that work done by Valentin. And so try to compile as much native code in advance as possible so they can be cached and doesn't need to be recompiled again when you start a new session. Maybe in the future we will also have a better static compilation story. There is some effort to like compile small applications, compile statically small applications written in Julia. It works well within some constraints, which at the moment are very, very tight. But maybe at some point in the future we will have like a better way to statically compile some applications. One problem in using MPI on A64FX is that custom reductions operations in MPI.jl at the moment don't work on ARM, so including also A64FX. This can in principle be fixed, but someone needs to do this work. And the last time that we gave this presentation, there was also this point that we need to have a runtime detection of support for single precision numbers. But since the last time that we gave this presentation, this work has actually been done. So now Julia, and also in the version that is available on Okami, Julia 1.9 will be able to automatically detect at runtime that it has native support for half precision. So it doesn't have to do some conversions between half and single precision for all the operations. And this has been tested also on AVX 500 single precision. And I think that's it from me. And
Thank you, Mr.
didn't see if there are any questions.
I've been answering some in the background.
Okay.
I think one of the most interesting ones was why is the compilation latency a problem in A64FX? And we're about to see some of that. So compilation latency, compilation in general is a little bit of I wouldn't say mostly. There are definitely parallel aspects to it, but generally speaking, it's a single-threaded problem. If you could have one big function that you want to compile, there's not much parallelism you can exploit there. If you have many small functions that you want to compile, yes, you can exploit parallelism there. So the A64FX is a really nice chip if you have a very parallel application, but if you have single-threaded bottlenecks like compilation, then you will notice that. And so, like as an example, so I'm about to do a couple of Pluto notebooks. These are actually all uploaded to GitHub Julia on Okami, where we keep this material, and we also put copies of the slides that we just presented. And so Pluto is an Julia alternative to Jupyter. While we are big fans of Jupyter, it has a couple of downfalls, and one of those is that when you change one of the cells, nothing else changes with it. And so I had it too often happen that students handed in notebooks for their homeworks and they didn't reproduce on my system. And so Pluto is careful about that. It tries to reevaluate code when you start changing it. And coming back to my original point, what I noticed when I first started Pluto is that everything is just a little bit slower than I'm used to. And that's the difference in the single core performance, because these interactive kinds of works can't take advantage of the A64FX architecture. Okay, so the three things I want to talk the two things I'm going to talk about for now is a little bit about benchmarking and trying to understand a little more about what the chip is actually doing. And so I'm going to import a couple of packages here. The most important one is benchmark tools. Benchmark tools is focused on micro benchmarks. So if your functions take hours to run, don't use it. But if you are trying to understand if a change that you're making to your code has an effect, benchmark tool takes many measurements in order to get rid of the statistical noise in the machine. Now, I often advocate against premature optimization. So first understand the performance of your code, establish what are the measurements that you care about. And if you don't measure, you won't improve. And so this is benchmark tools, but we're going to talk about. But if you care about profiling, we have an inbuilt statistical profiler that you can directly use, and there are different ways of visualizing it. Profile view is it's a common way, and I've been working on a little package that uses the Go infrastructure for analyzing profiles, pprof, that allows you to have a little bit more insight. On top of that, you have Julia integrates into some of the native profiling tools. On Intel, it's vTunes. And on most Linux machines, and as an example, on Okami, you can use perf. And if you enable the right flag, then you can even see into the just-in-time compiled traces. Another very fun tool is Liquid. Liquid is developed in Germany, and it simplifies massively the complicated question of getting performance counters, measurements for snippets of code that I might care about. And then MC Analyzer, if you are trying to understand why LLVM is making certain decisions, why it chooses to emit a certain assembly sequence, you can use MC Analyzer to basically back engineer why it assigned which slot it assigned in which place. So the central macro to use is @benchmark. @benchmark will repeatedly evaluate your code to gain enough samples. You probably will want to use the $sign in the context of the @benchmark macro to escape your input data to only measure the program and not the data axes. And so here I have a very small sum function. And I added a little bit of type annotation, but those type annotations are not normally necessary. And so when I use @benchmark to measure this, I can see that I'm getting a slight bit of a distribution, but generally speaking, actually, maybe let's increase the data size a little bit. And you can see that now automatically Pluto is rerunning the notebook and rerunning the cells that are dependent on this variable n. And yeah, so generally speaking, it looks like Okami, or the node on Okami that I'm currently using, it has a lot less noise than I'm normally used to. Yeah. Okay, so this is very useful, and this is also kind of why I like Pluto. It allows me to do a little bit of interactivity in my experiments and my presentations. Now, if I wanted to figure out what this function sum is doing and how the Julia compiler is analyzing it, I can use the reflection macros that I've talked about earlier. And so as an example, if I use @code_lowered, you can see this is the linearized IR. So we no longer see the control flow. Instead, we've replaced if and for with the eternal sin of all compiler writers. We don't believe in control flow. We just use gotos and then tell everybody else that they're not allowed to use goto. And you should not use goto. But it makes it a lot more, a lot easier to have one concept to analyze instead of having 3 or 4 control flow concepts to analyze. And so these are called basic blocks. And these percentage variables are called single static assignment variables, and these add variables and the x, they use proper full variables. And so after lowering, after linearization, Julia will do other analysis on top of that and then translate it to native machine code. Because this is a little bit complex, it's still a very simple function and we could analyze it to no end. Let's step back and make it an even simpler example. Instead of summing some data that has been given to me by the user, right? This x is a vector of some floating point numbers. Let's just count from 1 to n. And if I run this benchmark with a large enough k, you can see that apparently I'm very fast. So it takes about 32 nanoseconds to do 100 million additions. Well, if that were true, that would mean our processor operates at about 3 petahertz. So petascale computing would be already here, and we would not need massive supercomputers. A single core on Okami can solve all of humanity's problems. Well, if you're getting results like that, there's probably some compiler trickery going on. So always do this basic check. What happens if I'm using a 10x bigger input? So I now increase the input size by 10, and it turns out the time it takes to solve the problem does not go up by a linear factor. So you're not measuring what you think you're measuring. So let's explore what code is actually running. So first of all, we go back to @code_lowered. We can see here there's ACC equals ACC plus 1. That's our increment. Then we have this comparison here that looks like it might be the back branch of the loop. So we're gonna check if that condition is true. If that condition is not true, we will jump out of the loop, go to the return statement, and if it's true, we will go to basic block number 3, and then we will jump up to basic block number 2 and start executing this code over and over again. Hey, that's what I thought I wanted it to measure. So the next step is I want to understand what Julia sees here. When Julia runs its analysis, what did it infer? And so as an example, we can infer that because we are assigning ACC to be 0, that at this point the variable is indeed a constant 0. We know that this is a Boolean. We know that this is a tuple of integers. We know that the accumulate operation is also an int64, and so forth. So this is done with optimize equals false, or you can also do add code 1 type. Maybe. Okay. There we go. Right, and this is now trying to do a little bit of pretty printing. It's printing this in yellow, in order to tell me that this union might be something I want to look at. But yes. So if I look at what the Julia compiler actually does to this, I can use optimize equals true to the add code type macro, and we see that all of the code typed, that all of the function calls, the base.iterate, the plus operation here, all of those disappear, and instead we end up with these funny looking functions which are signed less or equal, signed less and equal integers, signed less than integers, add integers, not integers. So these are so-called intrinsics, and they basically map to LLVM instructions in the end. So this simplified the entire program. It inlined a lot of functions, and we end up with a much more simpler representation of the code, but it still looks like we're doing our +1 operation. So the compiler at this point has not figured out, I don't need to do the work. We still have a for loop. This time it is the go to 10 that is jumping back up to this block, then running the add int instruction, and so forth. And this add int is the one that I care about. The one thing, if you ever see this weird phi node in a compiler in Julia, it is literally a Unicode phi in LLVM. It is written out as a phi. This means that there is some control flow that is being unified into one value. So as an example, if you're coming from basic block 7, it will take the value true. If it's coming from basic block 8, it will take the value false. And so then I can look at what Julia emits to LLVM, and this, yes, Tony, we are looking at SSAIR at this point. And then we translate that Julia SSAIR to LLVM SSAIR. And we can look through this, and this is the Julia code generator being at work. It does a whole bunch of work in order to set up a function. And then we have a funny phi node again. And somewhere we probably do an add operation. Somewhere, find it in the C here. There is this. There's our add of the value phi operation. Now, the compiler still seems to do the work, so let's look at it after optimization. When we look at it after optimization, we figure out that, oh my, all of my code, besides the Julia sets up a function, has boiled down to check whether or not the value is 0. If the value is greater than 0, return the value itself. If the value is less than 0, return 0, and return that value. So it basically figured out that our wonderful loop here is either 0 if we never execute the loop, or it is n if we execute the loop. And then I can also do the next step, and I can look at what is indeed the assembly instructions being generated for this. And here we have our weird compiler barriers, and I'm less fluent in ARM than in x86, so you forgive me that I don't point out the place where we return the input value. So if you all have some, let's take a second. We can all basically sign into Okami. You can
Sorry, can you enlarge the font a little bit? It's yeah, yes. Thanks.
We can not mistype the load command and fire up a Julia instance on the login node, because we're not going to do any big computations. It's okay for today. So and let's take 5 minutes, and I will ask you to look at these functions G and H that look very similar to the function that we just looked at, but are a little bit different. And we're going to briefly talk about what makes them different and what's important here to think about. And if you were looking at my screen at the time, you saw the slight bit of compilation latency. Tony asked a question in the chat if Julia has strict indentation rules or it is more courtesy. We do not believe in white space sensitivity. It is customary to use either 2 or 4 spaces. In this case, when the ACC variable is a float, is not a float, in both cases, the compiler will not optimize the loop away. So if we look at code LVM of G, there's an awful lot of code, and we can actually see some vector instructions here. So the code is not optimized away. And if we look at H, the code is a little bit, we have less code to look at, but it's, we actually are doing vectorization. Fascinating. Scalable vectors are very weird. Okay, so the interesting aspect, I think, happens here if we look at the code typed of G. What I wanted to point out is ACC is one type. So ACC in the case of G, right, is an integer to start with, and then we use a floating point value to increment. And so Julia analyzes this and says, hey, by the way, ACC is either a union of float 64 or int64. Now, when I first wrote this example many years ago, Julia actually did not optimize this code very well. Nowadays, the performance difference is not that noticeable anymore, and it's kind of sad. I need a better example, but the better examples turned out to be very complicated. So this is something to look out for when you're optimizing code. People in the Julia world call this type instabilities. Because the compiler can't prove that the loop always executes, it doesn't know that ACC always should be a float. And it might be actually important that the first operation goes from integer to float. So we can't just eliminate that for you. And so if you look instead at the second example, H, it will tell you that ACC is always a float 64, and therefore there is no type instability here happening. If you look at the code, code type of G, you see these pi nodes here where we first say is 19 is a float 64, or if 19 is an int 64, switch which operations we are going to do. So we're basically inserting a check and say, hey, if the variable is this, do this operation. If the variable of this other type, do these other operation, and this is called union splitting. And for small unions, we now handle these nicely. Now, on x86, I wouldn't have expected these reduction operations to occur because for AVX it does not make sense. But apparently it is actually profitable on the A64FX, which is quite interesting because the thing I wanted to point out is that if you do an accumulation operation here, a plus equals 1, that the semantics must be that the accumulation must happen in order. And this is why what you see...
The reduction here is happening sequentially.
Yeah, the reduction, yes, I think we are still doing it sequentially. We're just doing it very funnily with vector operations. Yeah. So if I give the compiler a little bit more freedom, and I use the @SIMD macro, then I actually, the reduction looks slightly nicer, but it would need a little bit of investigation to figure out what is actually happening. Okay, so I hope you managed to fire up Julia and at least explore these things a little bit. But coming back to our original question, can we actually measure the speed of our original code? And I'm gonna make this shortish. The answer is yes, but we need to tell the compiler to not delete our operations. And so I've defined two functions here, clobber and escape. Clobber will tell the compiler that basically this instruction that doesn't do anything actually touches all of memory, and it can't reorder reads and writes arbitrarily. And escape tells it that this variable wall was actually observed during a function call, during the execution of the program. And if you're interested in how they are implemented, you can expand the cell and you can see that they are actually implemented by doing a little bit of compiler magic. So if you look at the function k here, it actually doesn't change anything yet. We now do a little bit more operations. I think we still do the for loop, but the ACC, the plus operation was the ACC, does not actually happen. And this is why we need our escape function, where we actually escape the value ACC. So we observe the value ACC at every loop iteration. And now we have 4 is our addition operation here that we are escaping. This is the loop increment. And so if you compare that with k, we do not have the variable increment anymore here. We only have the loop increment. So this is the add 4. And so now we are actually having a for loop that we execute n times. where we are doing n operations inside the loop. So we can measure this. We now get that this took 107 milliseconds about to execute. And if I multiply that by 10, I do indeed get that this now takes a second to execute. So the scaling, by increasing the amount of work, the amount of time that my program takes increases as well. And so this is a little bit low on Fugaku. I would have expected it to be roughly twice this, but at least we're now in the neighborhood. We're actually measuring something that is real. On my machine, on my laptop, it's about 4 gigahertz. And I wanted to make this point because I often see people who work on profiling benchmarks. You really need to first sit down and write down a hypothesis and be like, what do I actually want to measure? What is the behavior of the system I want to understand? Because if you're just interested in how fast F were, we would have been fine with our first measurement. And then we could have written out and wrote a wonderful blog post about the fact that Julia is a bazillion times faster than Python. But that would have not been the right message because, yes, Julia executes this function f very fast, but because it doesn't do any work. So if we are interested in the speed of addition as a proxy of performance, then we maybe need to be more careful in what we do measure. And the other comment is integer math on a computer is associative, floating point math is not. So if you give the compiler a little bit more leeway, it can often optimize floating point reductions much more efficiently, but it cannot do so by default because of IEEE semantics. Right, and this is the point here. If we look at H again, we benchmark H, we see that it takes about 500 milliseconds to be executing, and then we tell the compiler with the @SIMD macro that the order in which the iterations of the for loop happen is not important. It will go in and will mark all of these plus operations as reorderable, and as you can see, this increases the performance of our program drastically. And so these are called performance annotations in Julia. And so as an example, we do bounce checking by default, as I mentioned earlier. So if you have an array that is only of length 10 and you try to index the 11th element, that will be an error. But sometimes people care about the performance of a specific inner loop, and you can do a proof and say, hey, by the way, I'm going to check the bounds outside, and I know that my for loop, I convinced myself that the for loop inside is correct. And so you can put the @inbounds macro on a memory access in order to turn off bounds checking locally. And this locally really is key. If you look at C compilers, they often have global compiler flags where you can turn on the entire compiler and say, I don't care about the semantics of IEEE, I just want the fastest possible way of computing 0. And you can set a global fast math flag. Oftentimes you will see dramatic speedups, but you will sacrifice numerical consistency, reproducibility, and sometimes you will get plainly false answers. In Julia, we gone a different way, and by default, these @fast math options are only locally applying to your program. So you can choose and pick and say, okay, I know this function, it doesn't suffer from catastrophic cancellation. I can turn on fast math inside that function. Similarly, at SIMD, and it has an option called IVDEP. These are providing stronger guarantees to encourage LLVM to use SIMD operations. @SIMD is almost completely harmless. I have not seen a miscompilation with this for 5 years. @SIMD IVDEP is a much stronger statement. It says each loop operation is independent of each other, and so you can shoot yourself in the foot with that if you're not careful. Okay. So this is a fun notebook that Carsten Bauer at the Paderborn Center for Parallel Computing prepared. This is demonstrating the interaction or the integration of Liquid for performance measurements into Julia. And so this is running again on Okami. And so let's do some computation. We can choose what we want to do. We can say, hey, by the way, I want to add an add inbound statement here, or I can leave that out for now. And then I can use Liquid, but the important thing is that first, if I'm on Okami, I would look at my available modules, and one of them is Liquid. And one of them here, we have Liquid available. And I think a couple of weeks ago, maybe, the guys from Liquid also gave a presentation. And so I can load it. And now I have Liquid available. And so if I start Julia, and this is, by the way, the package manager, I can activate a temporary directory so that I have a new project where everything is clean. And then I say add Liquid. It will now go hit the registry and download it, but it already has cached it for me. And so then I can load it, and now I have it available and I can do operations with it. I can use it to do performance investigation. So one of these things is I might want to actually, oops, I hit too much. Yeah, I want to do I want to measure how many double precision floating point operations this computation is doing. And so I can use the add_perfmon macro, tell it that this is the group of interest that I want to measure. And then I get a set of metrics and a set of events. And I can use that to, as an example, figure out that the actual number of performance floats are about 10,000 in this operation. And so I can change this code, and I can, as an example, say, what happens if I take the sign of this and we now do many more floating point operations, and so forth. Now, this sadly did not work as well as I was hoping to, because the infrastructure didn't quite work on A64FX yet, so we're gonna skip this, and I filed bug reports. So hopefully, eventually, we can also show you how to just generate an imperial roofline model and try to understand what the performance of your code is. This leads into, well, how do I do multi-threading? And we will talk about multi-threading in detail a little bit later. But just as a teaser, you can use the add_threads macro to parallelize a for loop. And it will automatically, if you pass it the static keyword, it will distribute the iteration space over all of the available threads that you started Julia with. And there's a Julia package thread pinning.gl that allows you to say, as an example, I want to pin all my threads that I have in a compact way. And so if I use Liquid and this little function here to calculate how much of the available memory bandwidth I'm able to take with 48 Julia threads here, I can do an empirical measurement. And right now I'm getting about a quarter of the theoretical bandwidth. This is also vastly dependent on the size of the work problem. And so I haven't quite figured out what the correct parameters is and need to investigate why we are only getting a third if I increase the problem size. But probably the LVM compiler is not quite at the LVM backend for A64FX is not completely perfectly tuned yet. On Intel, we get much closer. We get 85% of the theoretical peak. So at this point, I'm gonna break for questions again, and then Mosé is gonna talk about vectorization. If there are no questions, then Mosé, take it away.
Okay, so what's cool about A64FX is the massive vectorization that this CPU can do. When I got access to Akami, I was looking at the documentation, and I found these benchmarks developed, I believe, by Eva. I hope I'm acknowledging the right person.
Actually, it was Robert, but
okay,
I'm just the one who uploaded them.
Okay. So yeah, these are on the website, so I'm not doing anything special. I took this function and I compiled them. Yeah, there is the repo here, so there is also a Makefile, so you can load all the modules and compile them to into a shared library. This is what I did here in this repository. And what I'm doing then is to call these functions from Julia to compare the how the different compilers compare with the Julia compiler. In this snippet of code, like in these 4 lines of code, I'm actually generating, I believe, 24 functions using metaprogramming. So metaprogramming is a powerful feature in Julia. Valentin already mentioned this like eval construct that allows you to dynamically generate things. And here in a for loop, I'm generating 24 functions, which are the different functions in the shared libraries that I'm looking at. So for example, compiled with a GCC, LLVM, and Fujitsu compiler, using both the fast mode or not using fast mode. And then I defined here a macro. If you want to see, the code is hidden here inside, but you don't really need to know about it. So what this macro does is to generate the benchmark for you. So what Valentin showed before, this is done automatically. So I only need to say, evaluate this expression using vectors. I'm basically skipping the setting up stage of the benchmark because I'm generating these vectors X and Y automatically. So that then I can measure the time and then divide by the length of the array. So to get the average time for each iteration. So let's do the showdown. So I defined, so first of all, I'm using here a lot the vectorization in Julia, which is done using the dot operator. So basically in this expression, when you do the dot in all these operations, you're basically writing this for loop. Well, Julia is writing this for loop for you, but you write this single line and Julia will do this automatically for you. This is like a syntactic feature. And yeah, so the first function, which is in the in this here is the simple function is 2 times x plus 3 times x squared, which in Julia you can define in this way, single line, define the function, and then we can run the benchmark. So this is going to run the benchmark multiple times to get the average, and then we'll do the number that will spit out is like the average across the all the elements of the array. So these arrays have like 22,000, if I remember correctly. In this benchmark, 2,000 elements. So I'm basically taking the average time of running this expression and then dividing by 2,000. And we can compare this with the Fujitsu compiler in fast mode. And we can see, yeah, we are within a factor of 2. But if we use the Fujitsu compiler, not in fast mode, I think we should get much closer to the Julia benchmark. Oh, not too much, but yeah, it's a bit closer. But it's more interesting to compare with the LLVM because it's like a more direct comparison to what Julia can do. So in fast mode, it's still a bit faster. But if we don't use fast mode, I believe this one should be about the same. Still no, so still Julia is a bit of overhead for this function compared to LLVM and not in fast mode. Valentin already mentioned here that you can look very easily at the LLVM code. So for this function, simple, which does scalar multiplication plus addition to another vector, basically. We can see here there is a vector body and there are all these operations which are using the vscale instructions, which are one of the cool features of A64FX. But to do this, you don't need to do anything. So you just start up Julia on A64FX and LLVM will compile directly to these instructions. So yeah, you can look at the LLVM code or the corresponding native code, and we should see somewhere here there are the Z registries. Yeah. So we're doing the multiplication and the addition using the Z registries, which are the vector registries on A64FX. And then we can compare the inverse function, which is the second function in the example. And we can compare Julia with the Fujitsu compiler. So this one will take a time of the order of 10 to the -8, while the Fujitsu compiler is about 2 orders of magnitude faster. So what's happening here, I also discussed this a little bit in Slack the other day. So this was done using the fast flag, so -k fast. But if I just remove the -k fast flag and compile with O3 optimization, again with the Fujitsu compiler, I should get the same as Julia. Yeah, it's about the same. So yes, in this case, I believe that the Fujitsu compiler in fast mode is doing some trickeries to speed up the computation and making vectorization much easier and much more probable to happen. So in this case, the LLVM compiler in Julia is not doing very well, and we can also see that the shared library that I compiled with LLVM is doing about the same as Julia here. Yeah, the number is basically the same. And also in fast mode, the LLVM compiler is not doing much better, if I remember correctly. We can see in a few seconds. Yeah, so even using fast mode in LLVM is not doing better. So I will say that in this case, the fact that Julia is very far away from the Fujitsu compiler in fast mode is because it's not able, not even LLVM, not even in fast mode, is not able to generate super efficient code that can be vectorized very well. You can also see the GCC compiler if you want, but yeah, here I wanted to mention that the flag in particular in LLV in the Fujitsu compiler, which is enabling the big speed up, is this KFP relaxed, which is basically using a approximate algorithm for the square root and also the division and the reciprocal. In fact, if you look at the native code of this function in compiled with a Fujitsu compiler, it's using some native ARM instruction specifically for the approximate division. Something that apparently LLVM is not able to generate, not even when you use the fast mode. And again, you can look at the native code in Julia. So it is using some vscale, but it's not really doing it super efficiently. And again, the native code, it does have some Z registries, for example, here, and also the division here is done on Z registries, but it's not using as much as possible compared to the Fujitsu compiler. But again, I want to point out that in this case, Julia is really limited by LLVM. And in general is on par with the LLVM compiler. So what I always say is that we always hope that the LLVM optimization are upstreamed, and so we get them for free, basically. Also, I wanted to come back to the AXPY function that was in the first presentation that I did, which was basically a presentation based on the paper that we published, where we use this function. And yeah, so I can run these two cells. So this one is compiling the Julia code, and this is calling the Fujitsu BLAS library. And in this case, as you also shown before, Julia is actually a little bit better than when using the BLAS library by Fujitsu. I didn't even need to define this function, but just use the dot operator in Julia, which is doing all the vectorization work for us, because yeah, I get basically the same number as this old function. So again, sometimes with a simple syntax feature that Julia gives you, you get basically the same performance as writing all this function. And also you can look at the native code. No, so this is the LLVM code, but on float 16. So if we go to the vector body, which is around here, yeah. For the AXPY, we can see, yeah, that Julia is doing the, yeah, here it is, multiplication and addition on vectors and using vscale instructions. So this will be probably multiplied by, I don't remember, another factor of 2, maybe, to get the full size of the vector on A64FX. Yeah. You can also look at the native code, which is more interesting because here in LLVM, these two operations are like separate operations, multiplication and addition. But this is not the full story, because if you look at the native code, you can see this is actually doing the fused multiplication and addition, which is a single instruction instead of 2 separate instructions. And yeah, can you do any better in Julia? So for example, the have you seen that the inverse example was not performing very well? And also the sine function was not performing very well. I didn't show it, but it was basically the same gap with the Fujitsu compiler. But there are some ways in Julia there are some packages that allow you to do approximate mathematical functions like the fast mode. One of these is Sleeve Pirates. As usual, when you do approximate mathematics, be aware of it, use at your own risk. But if we compare it, remember that Julia, both for the sine and inverse, it was around 10 to the minus 8. But here we get much closer to the Fujitsu compiler in fast mode. We are within a factor of 3 from the Fujitsu compiler. So using in fast mode, so using an approximate algorithm to compute the sine. I mean, it's not very approximate because I did a comparison. For example, we can do here. So X is a vector of 2000 elements, and I can compare if pirates in fast.
My favorite thing about float 16 is that you can compare all possible floating point values. Sadly,
Yes.
can't do that for float 32 or float 64.
Yes. Yeah, so in comparing these two, they're approximate. So there is this operator which does the approximate equality between the two functions, but we can, for example, get the maximum of the absolute difference between these two, and yeah, it's basically 1 epsilon. Like it's only one last the last significant digit. It's only one unit on the last significant digit. So yeah, it is approximate, but it's not very far from the like real, let's say, real solution. Also, the same function is true. It's not correctly rounded, but the maximum accepted error is, I believe, 1 ULP. So basically, this has 2 ULP compared to the correctly rounded value. And still, this is getting within a factor of 3 from the Fujitsu compiler. So I will say that in this case, using a third-party package, you can get pretty close. But again, remember this warning. You can look at the also for this function to the LLVM code and lots of vscale. And yeah, if you will look at the native code here, we'll use many more Z registries compared to the default sim function in Julia. And I will very quickly mention that for profiling, there is this package called MC Analyzer, which is using a tool in LLVM for doing profiling of code. So yeah, probably Valentin can tell you more about this tool because I discovered this last week when I was looking at this stuff. But for example,
yeah, basically it is trying to it will take the cost model that LVM has. It will analyze the function that you give it, or that is within these mark star and mark end ones, and it will assume that you're in a steady state. And then if you're in a steady state, it will look at the ports that your CPU has, so the resources that it has. So you need to look up in some handbook what the heck A64FX PPR stands. And as was pointed out in the chat, it is not doing performance profiling. It is applying the cost model that the compiler has in order to basically tell you, hey, this is the reason why I generated these functions. Or this is at least what I think these functions should cost like. And sometimes if you have if your compiler does the wrong thing and a different compiler does it better, it might be because the cost model is wrong.
Yeah, so this is one option, and then there is also timeline. It should give you no, wait, where is it? Oh, it's not showing. What?
No, wait.
It should appear below.
Yes, it should. Sometimes things don't work. Always the danger of doing things live.
Yes. Yeah, this is analyzed again for the sign, but I wanted to see the timeline. Okay. Here you get the timeline, where you get again the native code, but also a funny. Not this one. Where is it? Oh, yeah.
Oh, it gives you life ranges.
Yeah.
Nice. Yeah. One can spend a lot of time staring at assembly code. Generally, I don't recommend it. I recommend looking at LLVM IR first, but because most people don't have really like building up the intuition of what the CPU is doing at any given time is really hard. And so looking at the LLVM IR and seeing whether or not that makes sense, whether or not it vectorized correctly, all of those decisions have a lot of impact, and then instruction selection happens afterwards. but I had a case earlier this year where a student of mine was working on work stealing queues, and he ran into problems, and that ended up being a difference in instruction selection between AMD and Intel. And the instruction selected for AMD was a lot slower than the one for Intel.
Yeah, I think this is from this presentation. I just want to mention this tool. Yeah, it's really not the best one to use, but it is available.
Okay, so now I'm going to briefly talk about multi-threading, and then Mose is going to finish us out with talking about MPI. So multi-threading in Julia, I touched briefly on it earlier. We have the concept of parallel loops. What I want to point out is you start with using base.threads. It is a horrible misnomer. I would have preferred if we didn't talk about threads, because multi-threading in Julia is based on task parallelism. So I can use HWLock, and I can look at the topology of my machine, and I can see that I have 32 gigabytes of RAM, and can go upwards and see how it is split up. And then I see that I have 48 cores, and the A64FX does not do any shared multi-threading or any hyper-threading. So I have 48 processing units. And I can use the endThreads function to query with how many threads Julia was started. So if you start Julia yourself, you might want to set threads equals auto, so that you also get automatically the number of threads. Or you can say, I only want to start it today with 4, or I want to start it with the number of threads that Slurm assigned me. Right, so parallel loops, and they get, if we use threads as it is right now, you can see that I look at the thread ID. It's important to note that the thread ID is not guaranteed to be constant between in an iteration anymore. So the for loop is going to be split into a bunch of chunks. Each of these chunks is going to be assigned to a task. A task is going to be executed on a worker thread. And if the task suspends, then our different worker thread can pick it up later. In this case, though, everything gets assigned, but if you look closely, we notice that the order of threads is pretty much random. And so if I do static instead, the assignment of thread to chunk is statically given. And generally speaking, if you're writing general purpose code, I would strongly encourage you not to use static and instead use dynamic, because it composes better. So as an example, if you have experiences with OpenMP, there is often the question, so what happens if I have a parallel OpenMP within a parallel OpenMP section? And so as long in Julia, you have the same question with for loops here, but essentially speaking, I can nest add threads arbitrarily, and it will do dynamic scheduling to get your reasonable performance. This is the high-level for loop, where you can annotate it with the threads macro. Also important to note is what will happen is that we take the body of the for loop and we outline it into its own function, and then we will call that function on each task. What I can do instead is use task parallelism directly. So if you ever use Silk or TBB, that is our old task parallel mechanism. OpenMP tasks exist as well. And so I can say, spawn this Fibonacci function here, 1/2 of my computation, spawn that up, then do the second half of my computation, and then at the end, I fetch the result from B, and add it together and return that. Now, if I had done first A and then B, I wouldn't have seen any performance benefit, because we need to first spawn off the work and then do the alternative piece of work. So that's something to keep in mind. This is, of course, not the most ideal way of calculating the Fibonacci function, but it is a good example to demonstrate task parallelism. Now, if you ever looked at Go, you know that Go has channels to communicate between. These channels are basically communication pipelines. I can put a value in, and then somebody else can pick it up. So as example here, I spawn off 10 tasks, and each of these tasks will put a random number into my channel, and then I can collect all of the outputs. So if you have more unstructured computation, if you have producer-consumer pattern, you can use channels to communicate across tasks. Now, with using multi-threaded or shared memory processing, you suddenly get into the territory of race conditions. And so as an example, I can create a struct. I think that's our first struct we see, and I make it mutable, so I can change the context of the struct. If I remove the mutable, the content of the struct is not changeable, it is immutable. And so now I spawn a bunch of tasks off, and each of these tasks basically just increments a value in my counter. And if we look closely, apparently on a lot worse than locally, I only see about 11% of the updates. So this value in the counter in the end should be 10 times 100,000, so 1 million. And instead it was just about 100,000. Yeah, 100,000, so about only 11% of the updates. And the reason for that is, right, this variable x is not atomic by default. And so all of these updates race each other. And that's why we're missing so many updates. And to Tony's question in the chat, yes, the programming model is Silk inspired, but Silk or Go, it's more Go inspired than Silk. If you look closer, but we work a lot with the Silk people working on optimizing parallel programs. So instead, I can make the field atomic. Now, if I then use an atomic increment operation, I get all of the updates propagated correctly. Now, what happens if I have an atomic field and I want to increment it normally? And this is where we made some design decisions, and we said, as an example, atomic fields must be marked explicitly, and if they're used outside an atomic context, atomic store, we will present the user with a concurrency violation error, telling them that they must use an atomic variable in this context. You can read it non-atomically, I think. Yes, but you can't non-atomically update it. And you can also choose, because right, we're now on an ARM system. ARMs have a weak memory model, so you can choose what kind of consistency you want for your atomics. And there's a great talk by Jamison Nash that I linked earlier here, which is on YouTube, where he talks about a lot of these design decisions. And there's a big document out there where we describe the memory model that we went for. Now, one of the things that is not yet in the language is what to do with atomic operation on arrays, but sometimes you do need these, especially for scientific computations. And so there's a package called Atomics, which I included here in the beginning. And it's basically a superset of the atomic macro in base that also works on arrays, and it also supports user-defined arrays like CUDA arrays and other constructs. So we are working towards integrating this into base as a generic model. Now, when you're writing just these parallel for loops, you often get into this issue that you need to do a parallel reduction. And so a good colleague of mine, a good friend and colleague, Takafuma Araki, he wrote this package called floops.gl, and floops is a generalized parallel loop. And so instead of add threads, you say add floop. You then get the same construct, but you get an additional verb, an additional action that you can take. You can say, I want to do a reduction, and I want to assign the value into toad at the outside. And so it will basically turn it into a reduction tree and parallelize that correctly for you. You can make these things very, very complicated. I recommend taking a look at his documentation and tutorials if this is a problem that you run into. And then I can use this as an example to implement a parallel Monte Carlo pi calculation. Right, so we already briefly talked about this thread pinning, and it turns out that it has a whole bunch of options because you need to think about on different HPC systems, you need to think about NUMA zones. But on the A64FX, we have a single socket. Apparently, we need to double check that, or we need to check whether or not we need to subdivide every computational tile on the A64FX. But if you are on a system with more NUMA zones, you can choose how to assign the threads dynamically. So that was a very quick tour de force. One thing I will point out is that, as an example, the many operations in base are not yet automatically parallelized. And there is a package by Takafumi called ThreadX, which basically provides drop-in functionality for a lot of these base functions, like as parallelized sum, parallelized map reduce in general, that you can use. And over time, we are planning to integrate this into the language, but really it has been valuable to have a testbed outside where we can experiment with these things. And back to you, Mose, for MPI.
Thanks. MPI in Julia is not very difficult. So first of all, we need to load the module that we want to use. Again, on Okami, there are two different implementations available. I will go with MVA pitch. So in the repository that we shared at the beginning, there
do
is
you want to share your screen?
I'm not. Right. Right. Okay, now you should see it. Yeah, so you can load the module for MVA pitch and Julia. In this directory, I put this other directory which contains the environment. So the environment in Julia, in the package manager of Julia, is defined by a project which contains only the direct dependency of what you want to use in your project. And the manifest instead is like a full snapshot of all the packages present in the environment, including the indirect dependencies. So actually, we can also very quickly have a look at these files. So in the project, I'm only saying install the MPI package and MPI preferences, and you can also specify the compatibility bounds for these packages. So say install only packages which are compatible with these versions of MPI, the MPI preferences. Instead, the manifest is much longer. It's automatically generated, so you never ever need to touch this file. And yeah, it contains all dependencies with all the versions and so on. In addition to this, there is another file here which is called local preferences, which contains some information about like there is a package called preferences to say in my package, in this case called MPI preferences, we want to use the binary for the system which is called the libmpi, which has mpitch ABI, and to run it, I want to use srun. But you don't need to manually generate this file, but we can very quickly see how to do this. So I will start Julia specifying the project MVA pitch 2. Yes. So in the package manager, I should have already these two packages. But basically, after you load the MPI module that you want to use, in Julia, you do using MPI preferences, and then MPI preferences dot use system binary. And in the case of MVA pitch, we also need to specify that we want to use srun as a launcher for the MPI jobs. And so we need to pass also this extra argument. And this will automatically generate the file that we've seen before. So it's getting the information about the library available in the system, getting the version string, the version, and the API automatically. And then it has updated the file. Well, in this case, it didn't update it because it was already there, it was already the same. But if it had been updated, you would have to restart Julia. And now can do using MPI. And for example, initialize this. And again, with MVA pitch, we need to use the serial version of MPI. So we need to specify that for the threads, we only want to use a single thread. And just to check, I can get the processor name. Yeah, I am on this moment I'm on the debug node. So I'm getting the node of the name of this debug node. And then you can use all the MPI functionalities. So MPI.jl has two levels of API. There is the low level from where you can access the entire MPI API. And then what we recommend to use instead for the users is the high level API, which is a much simplified version of the MPI API. Do you see the bar here?
Your taskbar?
Bar. Yeah.
Yes.
Okay. I don't know how to move it, so okay, I can just shrink the terminal. So in the directory, in the MPI directory, I also put some examples which are taken directly from the documentation of MPI.jl. So for example, here there is a hello world, just to give you an idea of how to write MPI code in Julia. So you always have to do using MPI, initialize, define the communication, print whatever you want to print, and maybe have a barrier at the end. And to run this script, we go back to this directory. I put in the MVI pitch .sh script an example of a build script that the job script that you can use to run this to launch this script. So yeah, this is the regular slarm arguments that you want to pass for your script. And then module load slarm GCC MVI pitch and Julia. With this variable, it's very useful if you want to automatically set the number of Julia threads to the number of slarm threads. And then you run your job regularly, so srun. And then Julia specify the project, because the project again contains the specification of the preferences that you want to use. For example, I want to use MVI pitch instead of OpenMPI. And then the argument, the script that you want to run, which in this case is an example. And I should have the time to very quickly launch this batch MVI pitch 2.sh. Should be very quick. and we get the print. What was the print? Yeah, hello world from the name of the processor, and number of rank, and the total number of processes in this job. So yeah, we can see that we use these nodes on Okami. 1, 0, 1, 2, 3 rank out of a total of 4. And yeah, so this should give you like a taste of how to use MPI in Julia. Maybe I can very quickly look at another example. For example, maybe broadcasting. Yeah, a nice thing about the Julia MPI .jl package is that you can reduce the number of arguments that you pass to MPI. So you don't need to specify, for example, the types or the number of elements that you want to pass, because they're inferred automatically by the object that you're passing. So this is a dictionary, but like in an array, you only say pass the array A, as then the length of the array and the type of the array is automatically inferred from the object A in Julia. And so under the hood, the package is translating this information, passing this information to the MPI library. So this is all done automatically for you. And I guess it's like a nice interface to MPI because it has a reduced number of arguments. So like yesterday, I was trying to do some experiments with C. I also asked for help in Slack because I got an argument wrong when using the C API. Because yeah, I use this stuff in Julia, and I never remember all the arguments of the proper MPI API. Yeah, I think we are almost at the hour. So if there are any other questions.
Oh, thanks a lot, Valentin. It was really interesting, and I think for all of us, all the examples you showed, they are somewhere online, if I understood correctly. Can you put the link to that in the chat so we can access them and play around with it?